Hello, my name is Dongju Yu, and I'm a master student at GIST. This video is my presentation for the second homework assignment in MLDL course. Today, I'm gonna explain about generative models for classification. Let's begin. This is the index for my presentation in this video. First, I will introduce the problem we are trying to solve. Next, I will explain the core methodology, discriminant analysis. Then, I will dive into two specific methods, LDA and QDA. Finally, I will demonstrate the process of solving the initial problem using this method. Now, let's move on to the core question of this presentation. To truly understand the relationship between LDA and QDA, we will examine four specific problems. First, we will explore scenarios based on the shape of the true-based decision boundary. Question A asks if this boundary is linear, which model do we expect to perform better? We need to consider this for both the training set and the test set. Similarly, question B asks the same for a nonlinear boundary. This comparison will highlight the fundamental trade-off between the two models. Next, we will consider a more practical aspect, the effect of the sample size. Question C investigates what happens as our data grow. How does the test accuracy of QDA relative to LDA change and why? Finally, we have a true or false question that tests our deep understanding of model flexibility. Question D claims that QDA flexibility allows it to perform better than LDA even when the true boundary is linear. We will need to carefully justify whether this statement is true or false. In this slide, I will talk about the core idea of discriminant analysis, especially focusing on the generative approach. There are two main approaches to creating classification models. The first is the generative model approach, which we will be covering today. Prime examples include LDA and QDA. These models learn what the data for each class looks like. In other words, they learn the distribution of the data itself. You can think of it as creating a blueprint for each class. Mathematically, this is represented as Px given y, which models the probability of observing certain data x given the particular class y. On the other hand, discriminant models like logistic regression are different. Instead of learning the underlying distribution of the data, they focus on finding the decision boundary that best separate the classes. Mathematically, this corresponds to Py given x, where the model directly calculates the probability of a certain class y given the input data x. Discriminant analysis follows the philosophy of this first approach, the generative model. Therefore, its classification process is also quite intuitive. First, it learns the data distribution for each class. Then, when new data is introduced, it calculates the discriminant score for the data belonging to each class based on the estimated distributions. Finally, it classifies the data into the class with the highest score. So what is the LDA? The linear in its name means that the boundary classifying the class is linear. I will now explain in detail why that is. First, LDA is based on a few key assumptions. The first is the distribution of the data X for each class follow a Gaussian distribution. And this next part is the most critical assumption for LDA. We assume that the variance sigma square is the same for every class. This is precisely what makes the decision boundary linear. To keep the equation simple for this explanation, we will use only one predictor. Using Bayesian theorem, our goal is to find the class K that maximizes the posterior probability Py equal K given X equal X. The denominator in this formula is constant across all classes, so we only need to focus on the numerator. So we just need to choose the class with the largest numerator. I mentioned that we classify by calculating a score, and now I will explain how to derive the score. The score is obtained from the numerator of the posterior probability, which is the pi k, fkx. Based on our assumption, the class conditional probability density fkx is Gaussian, so let's substitute the Gaussian probability density function into the expression. Note that we use the common variance, sigma, because we assume it's the same for all classes. This expression is a bit complex to compare directly, so to simplify the calculation, we will take the natural log of the entire expression. Since the log is a monotonically increasing function, this won't change the final result of which class has the highest score. It conveniently turns multiplication into addition and simplifies the exponential term. Now, let's expand the simplified this equation. Here's an important insight. The term log 2 pi sigma and minus 2 sigma square x square are constant that do not depend on the class K. Since our goal is to compare the score for different classes, any term that common to all of them won't affect the final decision. Therefore, we can remove these terms. After removing the constant term and rearranging the remaining ones, we finally arrived at our desired discriminant score, delta kx. Here's the equation of the formula of delta kx. This is the formula you can see on the slide. As you can see, it takes the form of y equal ax plus b. It is perfect first degree equation of x. In other words, a linear function. Now let's move on to quadratic discriminant analysis. As the name, quadratic implies the decision boundary is no longer linear, but rather takes the form of a quadratic curve. The only difference in assumption between LDA and QDA is this. While LDA assumes equal variance across all classes, QDA relaxes this by allowing each class to have its own difference variance. Let's see exactly how this small change transforms the decision boundary into a quadratic one by deriving the discriminant score. The process starts almost same to LDA. We take the log of the numerator of the posterior. However, based on the QDA assumption, we now use a class-specific variance, sigma k. If we separate the log term, the expression becomes like this. And here, the crucial difference from LDA become clear. In LDA, we could drop several terms that were common to all classes. But in QDA, the only term that is truly independent of the class k is minus 2 log 2 pi because the variance sigma k square is now different for each class. And here, the crucial difference from ADA become clear. In ADA, we could drop several terms that were common to all classes. But in QDA, the only term that is truly independent of the class K is log 2 pi. Because the variance sigma k squared is now different for each class. The log sigma k squared term and the coefficient minus 2 sigma k squared are all class dependent. This means we cannot drop this term. By remaining only the true common constant, we are left with the final discriminant score for QDA as shown on the slide. Now look closely at this equation. When you expand the x minus mu k squared term, you get a x squared term. This means the discriminant score delta kx is a quadratic function of x. In LDA, the coefficient of the x sigma term was the same for all classes, so it canceled out during compression. Here in QDA, because the variance are different, the x squared term remains. Since the discriminant score is quadratic, the decision boundary where two scores are equal become a quadratic equation. This allows for much more flexible and complex decision boundary. Okay, so far we have looked at how ADA and QDA work individually. On this slide, we will summarize their key differences in a table. Every difference stems from this point, the variance assumption. ADA assumption assumes that all classes have the same variance, while QDA relaxes this assumption, allowing each class to have a different variance. This single change dictates the shape of the decision boundary. Thanks to the equal variance assumption in LDA, the x squared term in the discriminant function removed, and creating a linear boundary. In contrast, for QDA, the x squared term remains, resulting in a non-linear quadratic boundary. The shape of the boundary is directly related to the model's flexibility. Naturally, a complex curve is more flexible than a straight line, which is why QDA has much higher flexibility than LDA. Because QDA has more parameter variance, this flexibility leads us directly to the clash bias variance trade-off in machine learning. Because LDA is a simpler model with a strong constraint that the boundary must be linear. It has high bias, meaning it might not capture the true complex pattern of the data. However, it has low variance, meaning the model is stable and won't change drastically with different training data. Conversely, QDA is a more flexible model. This gives it low bias and it can better fit complex pattern, but it comes at the cost of a high variance, meaning it's more at risk of overfitting to the training data. Finally, this brings us to the quantity of the data for training. This closely relate to model complexity. ADA needs to estimate fewer parameters, just one common covariance matrix, so it can perform reliably even with a low amount of data. QA, on the other hand, need to estimate the separate covariance matrix for each class. To estimate these many parameters without overfitting, it requires a high quantity of data. In conclusion, neither model is always superior. LDA is a good choice when you have a small amount of data or when you believe the decision boundary is truly close to linear. On the other hand, if you have a large training data set and expect the boundary to be more complex and nonlinear, QDA will likely provide better performance. Okay, let's answer this question based on what we have just learned. The question is, if the base decision boundary is linear, do we expect LDA or QDA to perform better on the training set and on the test set? The key assumption here is that the true answer is a straight line. First, let's consider the training set. In this case, QDA will likely perform better. This is because QDA is much more flexible model than LDA. With this ability to create curves, QDA can bend and with each decision boundary to fit the individual training data points almost perfectly. Therefore, if we only look at the accuracy on the training data, the more flexible QDA will easily outperform LDA. However, it's a different story for the test set. Here, we expect LDA to perform better. Let's go back to the core condition. The true boundary is linear. LDA is by measure a linear model. This means that LDA's bias is assumption that the world is linear is a perfect match for the reality of this problem. So what happened with the QDA? QDA will use its high flexibility to try and capture every nuance of the training data, but it doing so, it runs a high risk of fitting the noise, not just the signal. This is where QDA high variance become a problem. The graph on the slide makes this clear. Imagine the true boundary is straight line, like the dashed pink line. QDA might overfit to the training data and produce a complex curve, like the solid green line. Why these boundaries separate the training point well is like to misclassify new point from the test set. ADA, on the other hand, will produce a straight line, like the dotted black line, which will be much closer to the true boundary. In conclusion, on the training set, the more flexible QTA will show better performance numerically, but on the test set, where we know the true boundary is linear, the simpler model that matches this reality, ADA, will be more robust, avoid overfitting, and ultimately show superior performance. This is a classic example of the bias variance trade-off in action. Okay, let's move right on to the second question. This scenario is the exact opposite of the first one. If the base decision boundary is nonlinear, do we expect LDA or QDA to perform better on the training set and on the test set? The key condition this time is that the true answer is a curve. First, the training set The conclusion here is the same as in the first question. Because higher flexibility allows a model to fit the training data more closely, QA will once again show a lower training error than LDA. Now, for the crucial part, the test set. Unlike in the first problem, this time we expect QDA to perform better. The reason for this comes down to bias. ADA is a high bias model, meaning it operates under the strong, rigid assumption that the boundary is linear. If the true answer is curved, but your model can only draw straight line, it will never be able to capture the real pattern, no matter how much data you give it. This fundamental mismatch between the model's assumption and reality is what high bias is all about. The graph on the slide illustrates this perfectly. And now let's move on to the third question. In general, as the sample size increases, do we expect the test prediction accuracy of QDA relative to ADA to improve, decline, or be unchanged, and why? As you can see on the slide, the answer is that we expect it to improve. Let me explain why from the perspective of the bias variance trade-off. As we have established ADA, ADA is a simple model with high bias and low variance. In contrast, QDA is a flexible model with a low bias and high variance. QDA great weakness is its high variance. This means that with a small training set, it runs a high risk of overfitting by learning the noise in the data. Because QDA has to estimate many more parameters than ADA, it's difficult to get stable estimates for these parameters from a small amount of data. However, the question introduces a key condition. The same sample size and increases. This is the perfect limit for QDA's main weakness. As the amount of training data grows, the parameter we estimate become more accurate and stable, converging toward their true values. In other words, abundant data acts as a powerful safety net that control QDA high variance. In conclusion, as the sample size increases, QDA's biggest weakness is high variance and risk of overfitting is diminished. Meanwhile, its great strength is low bias and flexibility to capture complex boundaries remain. Therefore, as we get more data, QDA's performance related to ADA will inevitably improve. This demonstrates a general principle in machine learning. More complex and flexible models require more data, and they can only unleash data unleash their true potential when that data is sufficiently provided. Now we arrive at our final question, which is a true or false statement. The question asks, even if the base decision boundary is linear, will QDA likely achieve a superior test error rate than ADA because of its flexibility? The answer, as shown on the slide, is false. This might seem counterintuitive at first. It is true that QDA is more flexible and a linear boundary is technically a special case of a quadratic one. So why does ADA perform better? The reason lies in the classic bias variance trade-off. ADA has a high bias. It makes a strong assumption that the decision boundary is linear. In this special problem, that assumption is correct. Because its assumption is correct and the model is simple, it has low bias variance. It doesn't get easily swayed by the noise in the training data. QDA, on the other hand, has low bias but high variance. Its flexibility means it doesn't just learn the underlying linear trend. It also tries to fit the noise and specific quirk of the training data. This is overfitting. To fully simplify, QDA needs to estimate more parameters than ADA with a finite amount of data. This estimation process introduces more error. While QDA could theoretically model a perfect line, in practice, its flexibility makes it train the noise in the training set, resulting in a boundary that is not perfectly linear and thus performs worse on the unseen test set. Therefore, because the model complexity of LDA is a better match for the true linear nature of the problem, it will achieve a lower test error. That's what I prepared for this video. Thanks for watching.